Hi, we're now in our last lecture on path dependence. And what I want to do is I'm going to relate path dependence to something else we've studied in this class, which is tipping points. And one of the really fun things about models is once we've got a bunch of models, we can compare and contrast them. And if we think for a moment about path dependence for tipping points, they seem very closely related concepts. So let's remind ourselves of what they are. What does path dependence mean? Path dependence means that what happens along the way determines the outcome. So formally we define this as outcome probabilities are going to depend on what's happened in the past. And we made a distinction between path-dependent outcomes. So does the outcome in this particular instance depend on what happened? And then path-dependent equilibrium. Does what happened in the long run depend on what happens along the way? So when we think about relating these to tipping points, it's this one we're going to want to focus on. It's these path-dependent equilibrium. It's the fact that like what happens in the long run depends on what happens along the path. Because let's think about how we define tipping points. When we define tipping points, we had two types. We had these direct tips, where the action itself moved things. And then we had contextual tips, like in the case of the forest fire model. So here I'm going to relate it to the active tips, the direct tips, where somebody takes an action and it changes the probabilities of things happening. So remember, an active tip, we started out with there's a 50% chance it could go to the left and a 50% chance it could go to the right. And then if there's a little bit of a tip this way, this then becomes 100% and this then becomes 0%. So this is saying the equilibrium of the system is now really likely to be over on this side, and it's not likely to be over here. So that's related to our notion of path-dependent equilibrium. So then the question is, what's the difference between path dependence and tipping points? Because in each case, it seems like something that happens along the way has an effect. Well, let's think about how we measured tips. A tipping point was a single instance in time where that long equilibrium was going to be suddenly changed drastically. So when you think about path dependence means what happens along the way. As we move along that path, how does that affect where we're likely to end up? So each step may have a small effect, but it's the accumulation of those steps that has the difference. With tipping points, everything sort of moves along in expected ways. We're not getting a lot of information. Then there's a singular event that suddenly tips the system abruptly from one case to the other. So when we measured tips, what we did is we had these measures of uncertainty. We used the diversity index, which just gave us a measure of sort of what's the sort of count or number of different equilibria we could go to. Or we used entropy, which was another measure we had that sort of told us how much uncertainty there was, how much information there was in the system. And when we measured tips, we talked about there being an abrupt change in the likelihood of outcomes. So let's see, just for fun, let's go back and let's look at our Polya process, and let's think about whether that really is path dependent or whether it has a tipping point, whether there's initial decision, whether there's sort of events along the way that have a big effect on what's going to happen. So remember in our process, right, we have an urn and we're picking out red balls and we're picking out blue balls, and if I pick out a red ball, then I add another red ball. So that's our Polya process. We want to see, is this thing path dependent or does it have these abrupt changes that leads to tipping points? Remember we got this result that says any probability distribution of red balls is in equilibrium and it's equally likely. So if we want to think about doing the Polya process and we think about how it works, so let's suppose that I draw 4 balls from the urn. And if I draw 4 balls from the urn, there's 5 things that could happen. I could get 0 red balls, I could get 1 red ball, I could get 2 red balls, I could get 3 red balls, or I could get 4 red balls. Now the probability of that, since we know from that previous claim, they're all equally likely, so the probability of each one of those is 1/5. So my diversity index, remember, was 1 over the square root of those probabilities squared. So that's going to be 1 over 1/5 squared plus 1/5 squared plus 1/5 squared plus 1/5 squared plus 1/5 squared. So that's equal to 1 over 5 times 1/5 squared. So that's 1 over 5 over 5 squared, which is 1 over 1 over 5, which is 5. But we already knew that, right? If you've got an equal distribution over 5 outcomes, the diversity index just equals 5. So the diversity index equals 5 when we start this process. Okay, so let's suppose that the first ball I choose is red. Okay, let's work through the math of what's going to happen. I could say, remember I'm starting out with 2 red balls and 1 blue ball because I'm picking the first ball red. And I want to ask, what are the different outcomes I could get? Well, one thing I could do is I could pick all red balls in the next 3 periods and end up with 4 reds. So what are the odds that I get 4 reds? Well, that's going to be, there's a 2/3 chance that this first ball's red. There's a 3/4 chance the second ball's red. and there's a 4/5 chance the third ball is red. So if I cancel all that stuff out, I end up getting there's a 2/5 chance of ending up with 4 red balls. Now I could ask, what are the odds that I get 2 reds and a blue? Well, again, here, 2 reds and a blue, it could go blue, red, 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 blue, red, or red, red, blue. They're all equally likely, so let's just do one of them. The odds of getting the red ball are going to be 2/3. The odds of getting the next red ball are 3/4, and the odds of getting the blue ball are 1/5. So if I cancel all this out, I get 1/10. But remember, there's 3 possibilities of that. The blue ball could be here, here, here. So I get that there's a 3/10 chance, 3/10, that I get 3 red. Now I could say, what are the odds that I get 1 red and 2 blue? Well, again, the odds of picking a red ball are 2/3. The odds of picking the blue ball are 1/4 for the first one, 2/5 for the second. So what I end up getting here is these things cancel out, so I get 1/15. But remember, again, there's 3 possibilities of where the red ball can be, so I've got to multiply that by 3. So that's 1/5, or that's 2/10. So there's a 2/10 chance that I get 2 red. And finally, I can ask, what's the odds, what's the probability that I get all 3 blue? And here the probabilities are, there's a 1/3 chance of getting the first blue, a 2/4 chance of getting the second blue, and a 3/5 chance of getting the third blue. And these things cancel out, and I end up getting 1/10. So what I end up with is the probability of getting 4 red is 4/10. Probability of getting 3 red is 3/10. Probability of getting 2 red is 2/10. And the probability of getting 1 red is 1/10. So this is my new probability distribution. So let's go back on computer diversity index. So remember, initially, this is what we had initially. We had a diversity index equal to 5. Now we've got 4/10, 3/10, 2/10, and 1/10. So how do we compute the diversity index? We just take 1 over 4/10 squared plus 3/10 squared plus 2/10 squared plus 1/10 squared. And that's going to equal 1 over 16/100 plus 9/100 plus 4/100 plus 1/100. So that's equal to 1 over 30/100, which is equal to 100/30, which means that now our diversity index is 3 1/3. Well, if we think about this, we start off with a diversity index of 5. Now we have a diversity index of 3 1/3. So this movement from 5 to 3 1/3 suggests that something that happened along the path affected where we're going to go. There's path dependence, but it's not an abrupt tip. An abrupt tip would be if we went from 5 to, say, 1.2 or 5 to 1, where one single event got rid of a whole bunch of uncertainty. So really the difference between path dependence and tipping points is one of degree. When we think about path dependence, what we mean is things along the path change where we're likely to go. So we move from, this set of things to this other set of things, but in a gradual way. Tipping points mean that there's an abrupt change, that there was a whole bunch of things we could have done, now we're likely to move to something entirely different, or something that was unexpected, or that uncertainty got resolved because of what's going to take place. Okay, so we've covered a lot here with tipping points. We've covered path-dependent equilibrium, path-dependent outcomes, path dependence, fat dependence, Markov processes, chaos, increasing returns, and now tipping points. And we've done most of this using simple EARN models, which is nice, because there's a lot going on in this area, right? There's a whole bunch of different concepts related to path dependence, but the nice thing is most of the stuff we were able to understand through this very simple model using EARNs. And this is one of the real advantages of using models, right? We had this sort of amorphous idea of path dependence. We thought it was related to something like increasing returns. It also seems somehow logically close to notions related to chaos and to tipping points, and it seemed not unlike our Markov process model. What we were able to do by constructing these simple EARN models is to flesh out all those differences between the concepts and really get a deeper, more subtle understanding of exactly what path dependence is, and even use some of our measurements for tipping points to see exactly how path dependence unfolds. Okay, thanks a lot.